let us now see how we go about simulating the battery charger circuit with current control, with slope compensated current control. So let me open this charger schematic in GSM. So this is the schematic that I have for you. pv.sub, I think you are now familiar with how to include the subcircuit file. Now this is the schematic. I discussed, while discussing in theory, I discussed about the buck converter. But here in the implementation, I thought we will use the buck boost converter. This is the buck boost converter circuit, so that you will get familiarized with one more converter in doing current mode control. So we have this photovoltaic source. It is the same source that we had modeled earlier. A short circuit current of 2 amps, voltage scale factor of 20, and then I'm having a buffer capacitor CT. These VIPV with value 0, VIQ with value 0 are the current sensing voltage sources. I have a switch here. This is the inductor current, inductor current measurement sensor, diode D, and the battery. Observe that the battery is put in a position where here it is plus, 1 is plus, 2 is minus, because the buck boost circuit you will have a negative voltage coming across the output, and therefore you have to appropriately connect the battery terminals. And of course the load. Now, how are we getting the PWM signals for duty cycle control? This is the SR latch. We have discussed about that. Now there is this summing junction where I am having IL measured. So I'm using the sense. There is this source here and I am sensing it from that source. So you see that this is a B source, which is giving a voltage equivalent of the current which is flowing in the inductor. So voltage is equal to I current flowing through the VIL voltage source. So here basically I have a voltage equivalent of the inductor current, and I have the IL reference coming in here, which is IL ref minus the slope compensated sawtooth waveform. Now I have interchanged the plus and minus here. If I zoom in, you will see that I've made this plus, I've made this minus. This is to make a simulation block simpler. We had put a comparator here with a minus and plus with an inversion here, and this comparator block I have removed and then did a sign change here itself, minus and plus. The inversion caused by the comparator is brought forward, and I have inverted the sign here because there is a Schmidt comparator at the input to the SR latch itself. So that is the only change. Then if you go to the slope compensation thing, now here I am having a B source, and B source I am getting a voltage equivalent of V0 by L. L is 10 millihenry. This 1 microfarad is coming because of this. VB into CS by L. So that is the formula that I have used, that we have discussed. So inductor value is 10 millihenry, that's what I have used. So this is the formula. Now this voltage will drive this voltage controlled current source. So there will be a current that is coming out through this, and then it will be charging up this capacitor. And if you monitor the potential here, you will get the voltage equivalent of I slope. And every time there is a clock giving a pulse, it will also reset the switch, short circuiting the capacitor and discharging the capacitor. So you will get a sawtooth waveform. This sawtooth waveform subtracts from the reference waveform, and that is what is given as reference slope compensated reference. So this is exactly the block schematic that we are simulating, and here this VC in the case of MPPT case, it will come from the output of the MPPT controller and will define the IREF. So now let us simulate this. Here a point that you need to note is that this SR latch is introduced now. The subcircuit of this SR latch is included in pv.sub, and the symbol file for this is also included in the set of files and folders which I had provided as resource in the last week's session. This is a voltage controlled current source, VCCS, and it is a SPICE simulation block itself. So the rest all you are familiar with, and let us simulate this. So let me open the terminal window. Let me go to pvsim, the folder which contains all these files. I will generate the netlist first, charger.net, by executing the gnetlist, and then now I will run NgSpice charger.cir. So it will start simulating. Let it simulate, and after simulating we will look at some important waveforms. Let us plot the IL ref and the inductor current, and we will see. So the red one is IL ref 3 which is at 3 amps, and let me expand it. So, and the blue one is the inductor current. Now you see that the inductor current is not reaching up to IL ref. The reason is that we have a slope compensated modified reference which is falling down from IL ref value, and when it is falling down from IL ref value, the inductor current will cross it over somewhere lesser than IL ref value and change state, and then start into the downslope mode. Let us observe the clock waveform and the voltage across this CS capacitance. The voltage across the CS capacitance is supposed to be like a sawtooth waveform with a positive slope. Let us compare them and see if we are getting waveform like we studied in theory. So let us plot voltage of the clock and the voltage across the CS node. So let me expand that. Let me select a very small narrow region, and you will see that this red pulse is the clock pulse, very small duty cycle. So whenever the red pulse comes, there is a reset of the voltage across the capacitance CS, and then it rises, and again at the starting of the next TS cycle, clock pulse comes, reset, and then rises, and so on. You have control on deciding the duty cycle of the clock. So this is as per what we are expecting. Let us now see this modified IL reference, that is the slope compensated reference here, which is the IL ref minus I slope, and compare it with the inductance current IL. So plot. So let me plot the difference between these two and the IL. So it will appear something like that. Let us take a very narrow region so that we will be able to zoom it like that. Now here you see the blue line is IL and the red line is the modified or the slope compensated reference. So you see with the falling, whenever the clock comes in here, okay, then it starts falling, subtracting, again rises back. The IL ref was at 3 amps, and from 3 amps it starts falling down with the same slope as the inductor down slope. And you see the inductor current, the moment it hits this at the down slope, the SR latch changes state, switches off that device, and then the inductor is falling. So on, it keeps going. So this is also behaving exactly like what we anticipated, and you see that the inductor current is controlled to whatever value that you set. Now let us see the voltage across the PV panel and the current through the PV panel, and just check how much amount of power is being transferred to the load to charge the battery and the load. So if we check the power drawn from the PV panel, see that it is hovering at around 24, close to the peak power operating point. So therefore you see that adjusting this ILREF value plays a role in actually deciding the amount of power that is being drawn from the PV panel, because the battery potential is more or less fixed, more or less constant at around 12 volts. So in this way, this buck boost regulator that we have used here can be used as a slope compensated current controlled charger for the battery, drawing power at maximum power from the PV source. So I will let you to explore this simulation on yourself and try to gain more insight from this simulation schematic.